So basically, we finished the course. We know all there is to know about quantum mechanics. We know that everything is defined by the wave function. We know that any measurable quantity is defined by some operator. It should be Hermitian. The possible outcomes of this measurement must be one of the eigenvalues of that operator. The probability of measuring it is defined by the amplitude squared of this eigenvector. Development in time depends on the Schrödinger equation, and at the moment of measurement, that is decided stochastically. It's just a probability. We can't give a prediction what the measurement will give. We can only say that if we repeat the same measurement time after time, we will get a probability distribution which is equal to the amplitude squared. Great. So what I want to do in this lecture is basically several questions regarding what can we say about different operators. And with the main weight it goes upon operators that work in the continuum. We'll see that we have their mathematical intricacies that we have to really define and try to understand. Okay, let's start from an easier question. We saw in the previous lecture that if we measure something according to operator A, the wave function will collapse on the eigenvector, the corresponding eigenvector of the operator according to the measurement, and will continue to develop in time according to that eigenvector. Okay, let's say that I measure B after I measure A. Do I know something about B, or am I still in a probabilistic state? So the answer is, depends. If A and B have the same eigenvectors, pay attention, eigenvectors, not eigenvalues, then yes, once I measured A, I'm collapsing on that eigenvector. And if I measure B and the same eigenvector is also an eigenvector of B, I'll get some result corresponding to B with 100% probability, with certainty. If B has a different basis of eigenvectors, then I don't know what I'll measure. I'll get some probabilistic. Okay, so now there's a neat mathematical way to check if I have two operators, whether they have a common eigenvectors or they have different eigenvectors. One of them you could tell me, okay, calculate the whole spectrum of eigenvectors for one, compare it to the whole spectrum of eigenvectors of the second one, and see if they are identical. That's somewhat cumbersome. So in order to check it, we have something that is called commutation of let's say I have two operators A and B. The commutation of two operators is defined mathematical definition. Now, if the commutation is equal to 0, very simple. It's a mathematical test, and in a moment I'll prove it. Okay, so basically, what does it mean? Let's say I have operator A These are its eigenvectors and eigenvalues. So I have a set of eigenvector psi ai, and I have it has some set of eigenvectors, some set of eigenvalues that correspond to operator B. Okay, let's take the left side of this expression. And we use it on some arbitrary wave function psi. I can always write it down on the basis of psi b, right? Because it's a full basis, as we have learned in linear algebra. Any operator has a basis that fully spans the whole dimension, no problem. Okay. Let's assume that it's the same basis and calculate the permutation. So if it's the same basis, So the first step is the same whether it's the same basis or not. This will be confusing, so I'll use J, A, J. Okay, it's not the eigenvalues. Someone should have pointed that. Okay? It's some arbitrary wave function. It's not necessarily the same eigenvalues as written. Okay? Right, because I'm operating with B on the basis of B, so it puts out just the eigenvalue here. But it's the same basis for A. So I'll get here. Okay. Rewrite the same expression, the same wave function. Okay, so up to the order of Bj and Aj, it's the same expression. But these two are scalar, so I can switch them. So, in this case, if they have the same basis, I'll get zero commutation relation. Okay. Now, what am I missing? I proved that if they have the same, I didn't prove the opposite, so I'll leave it to you as an exercise. Not difficult, you can find it in any linear algebra text. Okay, so I have an algorithm how to check if I measure A, do I know something about B? If the commutation is 0, I know everything about what I'm measuring. If they don't commute, it's not necessarily that I'll know something about B if I measure A. It could happen that I have two eigenvectors that happen to be the same and all the rest are not. I can't rule that out. But it's not necessarily for every wave function. Yes?
But the values that you get, is it changing something about
No.
everything or not?
No.
If you get 1 or 2 or 3, it's the same for you? Like if you...
Let's see a small example. Trivial or something. Mission, so it can be a physical operation. Permission could be a physical operation. So on and so forth. You agree that these are the eigenvectors, the corresponding eigenvalues, lambda, say 1, 2, 3, 4. Same eigenvectors, but lambda, let's call it lambda A and lambda B. Okay. Let's say I had a wave function let's be explicit. Normalized to 1, all is good. That's a kosher wave function. If I measure A, I get with probability half the value 1, and with probability half the value 4. Right? Okay. If I measure the same wave function for B, so I get with probability half 2 and probability half 8. It's the same wave function. Okay, let's say I do here a sequence of measurements. I measure A. I got value 1. I know that my wave, this is my eigenvector. Next time that I measure B, I'll get 2 with probability 1. I'm sure to measure it. Let's do it in an opposite way. I measure 2. I'll get with probability 1 the measurement of 1. But it could be that in the measurement of this guy I'll get 8. and then I'll get 4 when I measure. So that I have no control about. The only thing I know, if I measured A or B, I know what I'll measure in the opposite case. Okay. So far so good. Oh, and of course you can convince yourself that the commutation here is 0. It's quite easy. Okay, let's go and find certain eigenvectors of well-known operators. The first one is the position operator. Okay, in principle, I know what I'm looking for. I'm looking for position operator that it operates on the eigenvector psi x0. What does it mean? That I measure it at point x0 will give me the value x0 times psi of x0. Standard, nothing special. The same definitions that I used for any operator and its eigenvectors and eigenvalues. Unfortunately, because X is a continuum, we'll run into mathematical problems, which we will solve somehow. I don't think that we really solved it, but at the moment, let's ignore it. And I want to simplify the problem. I want to first consider a discrete case. Let's assume that my space is discrete. What do I mean by discrete? Let's say I'll show it in 1D. I have a line with points on it, and it goes from minus infinity to plus infinity. The fact that it's discrete basically tells me that I can, it's countable. So if it's countable, I can represent it by just regular numbers with plus, minus, whatever. Okay? Still, I have infinite points, but they're countable. How does the operator, first of all, what is the Hilbert space? It's infinite, right? Because I have infinite points, but it's still countable. So I can give a label. Let's say the first eigenvector will correspond to a particle on point 0. Will correspond to point 1. So on and so forth. This is a bit ugly. And to simplify it, I just count from 0. Did I really change something? No. No. Just make life easier, because then I can say 1, 0, 0. Corresponds to 0, 0, 1, 0 corresponds to 1. These are the eigenvectors of the position operator. And how do I write the position operator? The cousin of what I wrote 5 minutes ago. It's just the operator. That's good. I defined the eigenvectors and eigenvalues in this discrete space of the position operator. If I measure the particle on site 2, I have this eigenvector, and I get the number 2 as the result of the measurement of the position. Okay, and if I insist on working on a real space basis, which is this, on a computer, this is exactly what I do, because a computer is always discrete. It's digital. Okay, that's simple, clear, and no problems. Life becomes problematic when I assume that I have a continuum. Unfortunately, we have no good reason to believe that space is discrete. So, still I have this 1D, and I have a point x0. And how should the eigenvector look like? Well, very simple. Perfect analogy to what I did in the discrete case. If I'm on the site, I'm 1. If I'm in any other point, I'm 0. You can see the beginning of the problem here. This is not a continuous function. To express it mathematically, Dirac came up with a function that's known as Dirac's delta function. And we'll do now a small detour into its mathematical properties, because you can see already here they're a bit subtle. this definition is already problematic, even if I write it in this way, from the simple reason it's not normalized. Because if I would like to normalize it, I'll take a dx, and if this is constant, I'll get 0. Because a constant times dx that goes to 0 is 0. So, and here I'm hand waving and not being exact, I basically have to have here something that goes to infinity, and anyone who likes rigorous mathematics, don't listen. If I multiply it by dx, I should get 1. Okay, so how do I express it in a way that is a bit more rigorous? Functions that if I integrate over it, I get 1. But where do I have here this property of x0? I have no x0 here. So I write it as minus infinity to infinity. Okay, here I have the facts that I'm talking about, the point x0, not just the point 0. And basically, same from the other. So if my point x0 is within the range of integration, I get 1. If it's not within the range of integration, I get 0. Okay. What else can I say about this function? Yeah?
You said it's function, but you said it's a distribution. So what is it?
Well, a distribution is also a function, right? Mathematically, it's a function that describes the distribute or the wave function amplitude. We will see shortly how it's connected to the usual ways that we are writing down wave functions.
I have a question.
Sure.
Shouldn't it be the delta function squared equals to 1?
No. It's a delta function. I didn't yet find.
Oh.
I'm at the moment discussing the properties of the direct delta function.
Oh.
Okay, in a moment we'll see how it's connected to a wave function, to a regular wave function. Okay. What else do I know? If I take some function f of x, multiply it by delta x minus x0 and integrate at the moment, although it's enough that it's in the vicinity of x0, what is the answer? Someone can guess? It's f of x0. Okay, let's discuss a bit mathematical properties of this function. Property 1. It's an even function. 0 here, 0 there. It's not 0 only at 0. What is delta of AX? Now, if you want to understand properties of the delta function, basically at the end of the day, this is the properties that I'm working with. So I have to see what happens to the integration of delta of AX. Okay, let's check. Okay, I just substitute. Nothing happens to the boundaries. So my conclusion is if I'll be a bit more careful and I'll think about the negative case, then I have a switch of check by yourself. Yep.
And if delta equals to delta of x equals to delta of minus x, then how is it that the integral around the specific x fs equals 1 and the integral
No, that tells here it's this property of the function, what you are putting in. It's not any x. If it's written here x minus x0, so it's even around the point x0, right?
Oh, so I mean specifically around the 0.
As it's written.
Okay, thank you.
Okay. So, another property. Let's say delta of some function. So as an example, x minus x0 is also some function. Okay, intuitively,
All the,
what do I have to check here?
all the zeros.
Exactly. The delta function will give you a non-trivial result only at points where the function takes a value 0. So basically, I'll write down so I have here a sum of simple delta functions at the 0 point, where xi actually you can see it's similar to what we did here, but I want to show you an explicit example. Delta of x squared minus a squared. So I go and check the points where this expression x squared minus a squared is 0. I have 2 points, a and minus a. Okay. So I can write down here according to the definition. Now another cute property. what is x times delta x? It's A. Always returning to the integral and performing it. As long as f is a well-behaved function. Okay, and the last thing before I'm this is connected already to your question because now I have two amplitudes multiplied, not the same. And I'll prove it in a moment when I'll use some different definition of a delta function in order to show this. It's not completely unreasonable what I wrote. At least for if A is not equal B, certainly I should see 0, 0. Okay?
So it's the same as saying like Kroneker's delta AD, right?
Mm-hmm. Same thing. This, to prove this point, we still need something. Okay? And, okay, what's our problem here? Basically, if we want to do real mathematics, or at least well-controlled mathematics, is this sudden jump that we have in the definition of the function at x equals 0, right? So what do we do in this case? What we usually do, we take some function that in the limit is a delta function. And we'll see in a moment that there are many different such functions, and one of them will be the most powerful or most convenient to use. Okay, so we're still dealing with delta functions. And I'm giving here a list of definitions. How do I know it? Insert it, perform the integration, take epsilon to 0, you'll get the value 1. And if you look on it, it makes sense because this guy is 0 anywhere except at 0. But this is a cumbersome definition. Nothing that has absolute value in the function is easy to work with, as you probably have seen in your mathematical courses. It always causes some ambiguity. Okay. Again, if we'll just look on it, everywhere that x is not equal 0, you take epsilon to 0, it's 0. Because it's 0 divided by something finite. The only problem starts when x is defined as 0. Then you have here 1 over epsilon, and if you take it to 0, it diverges and then checks the integral. Again, it's not something we'll work with, so I won't go into details. Something a bit more basically it's similar to this definition where I saved the absolute value by taking x squared. And the definition that we will use, and we will investigate now in more details, looks ugly, right? Sine of 1 over epsilon means that if I go to 0, I get very dense oscillations at the area of 0, right? Change x by a bit, I get very dense oscillation. So first of all, which I didn't prove about it, we know that delta x dx minus infinity to infinity has to be equal to 1. So if I claim that this is a definition for delta at the limit that epsilon goes to 0, I have to have that the integral limit of epsilon goes to 0. Should have written here also these limiters. Okay. Someone has an idea how to perform this integral? Complex numbers. Okay, well, why is it connected? Okay, so now I'm in the complex plane. So I'm looking on here. Just the definition of sign. And now let's look on the following contour. When I'm working in a complex plane, I'm usually trying to do an integral by drawing some contour, finding the poles, and claiming that the integral over the contour is equal to the poles within the area that it encloses. That's a whole game I'm usually doing. Okay. So this is the contour I want to do. Going from minus infinity to infinity, which is the integral I'm interested in, and adding a piece that I don't really want, but I have to have it in order to close the contour. Now, let's examine this part. Okay, this part goes along the positive part of I to the power of what, some imaginary part. This will have zero contribution. Great, so this contour is equal to this integral. Nice. Okay, but where are the poles? The pole is only at 0, right? I don't have any other point where this guy goes to 0. So, what do I do in this case where the pole is exactly on my contour? I perform here a small roundabout, calculate this part of the contour, and get here value minus IP pi and basically you're not proficient in complex integrals, you don't follow exactly the steps that I did. Not extremely important unless you want to be 100% in this definition. I won't do anything more about these integrals. It was just to prove that the integral goes to 1. So if you need additional steps, open any math textbook that it will give you such an integral. This was just an illustration how I do it. But there is here something very important. And this will be a real useful definition that we'll use all the time. Repeatedly in quantum mechanics, in anything that has to do with fields, in condensed matter, which you will take next year. All of them will use this definition repeatedly, and actually you already know it, but you don't. What do I mean? Basically, I will show you a different way to do a Fourier transform. Why is it connected? Okay, I want to rewrite what's written here. Okay, this is the definition. Okay. Limit that I'm always forgetting. Why? Just performs the integral. Leave epsilon finite. Perform this integral because this integral is easy to perform. What is it equal? Just an exponent. I know to perform an integration on an exponent. If you're not convinced, just perform derivative. You'll see that you get back e to the power ikx. Insert it. Okay? Integration was over K, so I insert every place that K appears. Okay, and this is just this divided by 2I is exactly sine. So So what is the delta function? Fourier transform of a constant of 1. Remind yourself what is the definition of a Fourier transform. That's it. Now, this is an extremely convenient way to calculate something. For example, the things that I left unproven 10 minutes ago, 15 minutes ago. Basically, I asked what is minus infinity till infinity dx delta x minus a times delta x minus b, right? Just quoting definitions of delta functions. So I exchanged the order of integration. did I do here? Just remove the parts of the exponents that don't depend on x prior to the integration. Okay, so all this remains the same. I want to do here a small rewrite. What is this guy? It's a delta function. So this guy, by the definition that is erased now, is delta of k plus k prime up to 2 pi. It's 2 pi.
Why do you have 2 pi?
Because it was defined as dk delta is 2k x is equal to 2 rho dk 2 pi e to the power I k x. So here the integration is on x, but I have to somehow bring the 2 pi. So I divide by 2 pi and multiply by 2 pi in order to get the definition. And pay attention, here's the delta is on k, because the integration is on x. Great. Okay, let's perform the integration on k prime. Any integration where you have a delta function is an easy integration, because all you have to do is put the value of the function at the point where delta is equal 0. Okay. Okay, so this I just copied. I'm performing the integration on dk prime. 2 pi falls off. Right? Because the only thing that the delta tells me, instead of integration on k prime, insert k prime equal minus k. That's exactly what I did here. And this, by definition, because minus x is equal to x. Okay, so we see that integrations where you have delta functions, if you don't know to perform them, write them down in this form. Just go step by step in the integration and you get the result. End of story. Okay, so after this long mathematical introduction, we're ready to go back to the eigenvectors of the position operator, which was our goal. And we'll do it after the break. Let's see. Okay. So, what is the eigenvector of the position operator? Now, the operator x, as we defined it a few weeks ago, is simply x. But this, by definition, as we have written down a few minutes ago, so the delta function is definitely the eigenvector of the x operator. Okay, but I need two other properties of the eigenvectors, and that is orthogonality and normalizability. Okay, orthogonality. Okay, these are two eigenfunctions. Delta at x0 and delta at x1. But we just solved this guy. If x0 is not equal x1, it seems okay, it's 0. If x0 is equal x1, we have a problem. It's not normalized. We should have gotten 1. Okay. So what do we do here? As good physicists, we ignore this problem with an asterisk. What do I mean by ignore this problem? We come out with a statement for continuum. We don't have the usual orthogonality. We have Dirac's orthogonality, and we call this Dirac's orthogonality. What does it really mean? It means that the eigenfunction of the position is not within my Hilbert space, because Hilbert space must be normalizable. So I can't get it an exact value of the position through a measurement in my Hilbert space. And now we internalize it and forget it. We always say we measure position. In the meaning is that we get some distribution around point x0 when we measure position. If if you don't like it, go back to the discrete definitions. There things are clear, well defined mathematically, and although it sounds a bit stupid, you'll have bigger problems even when you are trying to do quantum fields theory. And you always go and say, first do it on discrete, see how it behaves, then pull the definition into the continuum. Okay. Not okay, but that's what we have. So the usual definition of Dirac's is if I have some operator the position is the definition, and lambda is a continuum, meaning you can get any value of lambda that you want, is not discrete. Then the orthogonality condition is actually a Dirac orthogonality. Okay, lovely. So, till now we are writing psi of x. I said that it's in the position representation, space representation. What does it really mean? Well, according to what we have learned till now, it has a very clear definition. Okay, it's a sum over the basis of the position with the appropriate amplitude. Right? That's any wave function I can write as a sum over the basis function, meaning the eigenfunction, with the appropriate amplitude. Great. There's one small problem. I wrote here a sum and we have a continuum. No problem. Let's write it down as an integral. Writing x prime so we won't get confused with this x. these are the eigenvector bases. So we know it's delta function. Integrals with delta function are easy, because this is the function times delta. So, writing down the wave function in this form is just writing down the amplitudes of the eigenvectors of the position representation. Nothing more, nothing less. So until this moment when we wrote down psi x, it was the amplitude. Now we know it's the amplitude of the eigenvectors of the position representation operator. So it's a deeper layer. For everyday use, it doesn't make any difference. Write psi of x, it's implicit that it's just the amplitudes appearing before the eigenvectors of the representation. Of the eigenvectors of the position operator. Okay. So what's cool about it? Basically, we can write the wave function also using other bases of other operators. Okay, for example, the momentum representation. I told you there's nothing basically holy about writing it as psi of x. Now I start to understand why. Because writing down as psi of x is for a certain basis. I don't like this basis. I can write it down according to a different basis. Okay. Now we understand also why taking psi x squared is the probability of finding it at point x. Why? Because that's the amplitude. Amplitude squared is the probability of finding it at this position. Okay, so if I wanted to take it into a different basis, I need the basis of some operator. We'll do now the basis of the position of the momentum. this is the definition of the momentum eigenvector, right? I operate with this, with the momentum operator, I get the value of the momentum. Why do I continue to write it in the X representation? Because at the moment, this is the basis that I'm working with. Same that I'm writing down 1, 0, 0, 0, just because this is the base that I'm working with at the moment. I could write it down under a different basis. Okay, so to find the eigenfunctions, I have to solve this differential equation from our vast experience in differential equations, what is this function? Excuse me?
Sine.
No. Come on, guys. This is an exponential. You perform a derivative, get some constant before it. This is simply an exponential.
Yes, but it has an I in the exponent, right?
Lovely. That's as good as anything else in the exponent. From the derivative, you get I times minus I, P0, H bar is cancelled, you get exactly P0 times exponent. Okay, this is the eigenvector P0. Okay. Orthogonality. I get a basis, I have to check orthogonality. Now, physicists are usually lazy and don't want to carry around this H bar, and therefore rewrite K as P over H bar. Okay, remember H bar times K is P. So I'm writing down this is our good old friend, the delta function. You have a continuum of values of momentum that you can get, therefore it's a variable with continuum eigenvalues, and you get the Dirac orthogonality condition, and all you need from that is basically you want to normalize it according to Dirac normalization. Add here 1 over square root of 2 pi. That's a constant. Okay. I'm sick and tired of working in X representation. I want to move to P representation, or as I said, as a lazy physicist, to K representation. Okay. I have my K representation. So psi of X what do I need here in order to write the wave function in the K representation? To find AK, once I know AK, I know the representation in the K basis. We have all the amplitudes corresponding to the eigenvectors of K. Good. So how will we do it? Well, Till here, the usual game of linear algebra. Nothing more, nothing less. Before I'm going to perform this integral, let's write it down specifically. Right? Do it not confuse it, leave it here. Right? Just wrote down the definition. What is this? No, mathematically, even before delta functions, what is this? The Fourier transform of psi x. What is AK? Without knowing anything, and in a moment I'll show it in a different way, which is the one that I started. So, let's change the order. This depends on the case, so I can pull it out. And through that, delta function. Nothing in creation is anything but a delta function. Even normalized correctly. So, this is simply AK prime, which is the usual inverse Fourier transform in order to get the amplitudes of K. So give me a wave function, and no problem, I'll write it down the amplitudes in K space or in momentum space. How will I do it? It's just by the inverse Fourier transform of the representation in weak space. Why is it connected to Fourier transform? Just because it happens to work on the same eigenvector. So it's actually, if you didn't think about it in this way, Fourier transform is nothing special. It's just a transformation from one basis to another basis, where in the original basis your representation were delta functions in one variable, and the other one is exponents in the same variable. Power IK. Well, I'll let you in on to a secret that actually will turn out to be very useful in the future. Any transformation from a basis to a basis could be some transform. Throw me a transform that you're familiar with. The plus, exactly. You have there a basis, which in this case is the exponent, not in the imaginary part. Same thing. So any transformation is basically a transformation of basis. Nothing more, nothing less. It has some orthogonality. Sometimes it's a more complicated orthogonality, and we'll run into such cases. But it's just an orthogonality transform between two bases with some orthogonality condition. So now, life's good. If I want to say what is the probability of measuring some value P0, no problem. Which is the Fourier transform up to h bar of the wave function given in the space representation. Nothing more, nothing less. Okay, two additional remarks. One, if you haven't noticed till now, we happen to live on a 3-dimensional world. So until now, I, for simplicity, kept everything in a 1-dimensional notation, but let's extend it to 3D. So I have the eigenvectors of the operator R vector, which is just delta R vector minus R0. And what does it mean? It doesn't make sense. Yes, if I do an integral over dr vector, it's dx times dy times dz, and you'll get the correct integral as 1. K for this case. Okay, note this dot product. Students have a tendency to forget about it. When I'm writing it shorthand in this way, it's not k times r. K is a vector and r is a vector. This is actually e to the power I k x x plus k y y plus k z z divided by 2 pi 3 Let's do it once so it will be completely clear. I want to check the orthogonality of k prime vector times k. Okay, nothing more than copying this definition. So I have outside 1 over 2 pi to the third. Now, dx, dy, dz, and usually no one bothers to write down this whole description, but once we'll do it, times e to the I k prime x minus, because it's complex conjugate, minus I k prime kx minus I k prime x k prime y minus I k prime z times e to the I k x x plus I k y plus I k z. What did I do here? Just copied this long and cumbersome definition. Okay, Fortunately, I have only dependence on x in one point, here and here, and y here and here, so I can rewrite it as 1 over 2 pi third. Okay, so I've written down the whole integral. Why is it kx prime minus kx and not the other way around?
Does it matter? We can switch that.
We can switch it, it's a stupid question. Okay, we have 2 pi to the third. Lovely. Kill this. We have delta k prime kx times delta k prime y minus ky and delta kz prime minus kz, which is delta of k prime minus k, which is a Dirac orthogonality condition, and therefore it's a good 3D basis for the momentum. Now, there is an additional point, and that will be the last point of this lecture. We saw that it's easier to understand what happens for real space if we are discretizing the space. What is the corresponding discretization that we can do to the momentum? And actually, here, discretization of the momentum has an interesting physical property. What does it mean? Discretization of the momentum in momentum space actually doesn't mean discretization of real space in real space. Well, actually, if you stop a moment, think about it. Sure, it's different bases. Surprisingly, if I take real space and take the 1D space and turn it into a ring, I discretize the K. Let's show it. So this is known as PBC, periodic boundary Okay. What are the possible eigenvectors of the K operator or P operator? Okay, we have already run into it. We are already experts. Now, if I have periodic boundary conditions, what does it mean? It means that if I'm at some point x and take a turn around and return to x, I'm at the same point, right? That's the meaning of periodic boundary condition. So this must be equal right? That's my condition. If you give me x plus L plus 2L plus NL, it has to, you return to the same point, you have the same function. Okay, so let me rewrite what's written here. So I can't get here any k, but only k's that give me what are these k's? Any multiplications of these conditions. And x equal 0 plus minus 1 plus minus 2. So k is discretized here, p is discretized here. Now, as a point of interest, how many of you have heard that in, let's say, string theory, there are 10 or 11 dimensions? Probably anyone who read any popular literature about physics has run into this condition, into this description. Well, why do those crazy people work in 10 and 11 dimensions when clearly we have 3? So their answer, whether it's right or wrong, I don't know. Nobody really knows. comes out that you have 3 large dimensions and one time and another 6 compactified dimensions. What does it mean? It means that there have periodic boundary conditions with very small L's. Now, how does it solve the problem? Because if I want to describe a wave function in this universe, which has 3 large dimensions and whatever, 6, 7 small ones, let's say, how will I define a free particles are? Write down this equation kx, ky, kz, add letters that you're interested in. Now, what values can this k take? If L is large or infinite, a continuum of values, the things that we are used to from everyday life. For a very small dimension, can take only a 0, which will be 0, and 1, which will be a huge value because L is very small. Now, if we think about writing down the energy as kx squared plus ky squared plus kz squared plus k whatever squared, these terms, when we are looking on low-lying excitations, on low-lying energies, won't contribute anything because I don't have enough energy to do anything in these very small dimensions. Therefore, it's not relevant for daily life. Perhaps if you go to extremely high energies, you'll see a manifestation because then you have enough energy to move into the next level.
They prove something? They couldn't prove this. Yeah.
Well, they have never seen it experimentally. That's one huge problem. The other problem, which, if you heard the term Yau-Kabali, once you have more than one curved dimension, you can connect it in different ways. Now, when they started discussing these problems of string theory, they had a hope that you'll have only very small order of 1 possibilities that are consistent of connecting these. Well, nowadays we know that basically mathematically 10 to the power of 500 such possibilities exist, and it doesn't tell us anything why we are living in the universe that we are living. So some people are happy with it. By chance, we have fallen into one of this periodic boundary conditions that we have. Some people are trying to convince that, well, there's only a very small subset that gives you conditions that life can exist there. That's a anthropic principle. Another says this is not a theory. A theory that tells you that basically there are 10 to the 500 possibilities of building a universe, and you have by chance fallen into one of them. Doesn't give me any information. That's not science. That's just mathematics. Doesn't help us anything. And that's where we sit today. But anyway, the point is that you can already see a glimpse of this behavior already in the very simple one dimension, one particle quantum mechanics. It has the seed of this. kind. Okay, we'll stop here and continue in the next week.
ביי, תודה.
Thank you.